Hello everyone, I hope you all are doing well. So today we will be starting with the chapter Application of Derivatives. Now in this chapter we are only going to be learning about differentiation and how can it be applied in different types of questions. Now mainly we are going to be focusing on graphical structures as to how you can talk about whether a graph is increasing, decreasing, or what are the different structures of the graph based on their derivatives. Now, the derivative can either be the first one, the second one, all those things. More or less, you will have to do differentiation a lot in this chapter, which we have already done in the previous chapter, which was limit, continuity, and derivability. Now, we will be looking into its applications. So if we look at the subtopics, first we'll be looking at what basically increasing, decreasing functions are, what are their critical points, local minima, global minima, point of inflection, nth derivative. Now again, this chapter is also not a very long chapter, a short and easy chapter. So let's start. So as we already know, our definition of derivative, this formula we had studied in limit, continuity, and derivability. This is basically the proof of how derivation is done or differentiation is done. So basically we try to find out, let's say if this is my f dash x, what do we write this as? Dy by dx. We try to find out our dy by dx by differentiating our function that has been given to us. And what does this dy by dx signify? It is the slope of the function that we are differentiating. So let's say if I have a function which is in this format, and if I differentiate it at this point, so I will get the slope of the line passing through this point, which is almost like a tangent to this point. So that is the main purpose of dy by dx, for us to find out the slope and check whether the graph is increasing continuously or decreasing continuously. So same things have been mentioned here. Rate of change, the derivative gives the instantaneous rate of change. So when we talk about dy by dx, it is basically the instantaneous rate of change. That means we're talking about the instant, at that very instant, what is the rate of change. However, there can be one more rate of change which we call as the average rate of change. And how do we represent our average rate of change? Our average rate of change is represented as delta y by delta x, where we consider an interval or we consider a range at which we are finding out what is the rate of change of y with respect to x. And again, talking about dy by dx is considered to be a very small number. It is almost tending to 0. However, when we talk about average rate of change, it is not tending to 0. It can be tending to 0, but generally it is not. Now again, examples of rate measures. In physics, you all have studied velocity is the derivative of distance. So we write it out, v is equals to dx by dt. Acceleration is the derivative of velocity, so dv by dt. So what we can say about acceleration is that it is the double differentiation of distance. So we can also write it down as in this format. So keep this thing in mind as well. Now again, as I mentioned, average rate of change measures the rate of quantities change over a specific interval. So for example, here they've given us x1 comma x2, this is our interval, and we have to find out our rate of change in this interval. So it becomes f of x2 minus f of x1 upon x2 minus x1. When we talk about instantaneous, so it is going to be at a certain point. So for example, here it is shown at x is equals to a. So if I was to represent this in dy by dx form, how can I write this down? This would become dy by dx given that x is equals to a. So this is how you generally represent instantaneous rate of change. And just to show you the relation between average rate of change and instantaneous rate of change, what we can say is limit x tending to 0, delta y by delta x. This is going to give us our dy by dx. So keep this thing in mind. Our dy by dx is a very small number, so keep this point as well. Now let us look at a question. A spherical balloon is being inflated at a rate of 35 centimeter cube per minute. Find the rate of increase of its surface area when the diameter of the balloon is 14 centimeter. So a spherical balloon is being inflated at 35 centimeter cube per minute. That means what they have given us, that the volume of this balloon is increasing at the rate of 35 centimeter cube per minute. So if I was to represent the volume by V, that means dV by dt, they've given us, it is plus 35 because it is increasing, right? And since this is a spherical balloon, that means for a spherical balloon, how do we write down our volume? For a spherical balloon, our volume is 4 by 3 pi r cube. Now let's say if I differentiate this, this would become dV by dt 4 by 3 pi. Now since this is a constant, it would remain as it is. R cube would become 3r square. And here we would have dr by dt. I hope you all remember this differentiation. When we are doing it in parametric form, that time we write dr by dt, since we are differentiating r in terms of t. So now from here what we can see is, we know the value of dv by dt, so we can find out our dr by dt. And what was asked to us in the question? Find the rate of increase of its surface area when the diameter of the balloon is 14. So they've given us the diameter, which is 14 centimeter. That means what we can say about our radius, it is going to be 7 centimeter. So from here, let us simply substitute the values and see what we are getting. So from here 3 and 3 gets cancelled out, and if I put dv by dt as 35, we are going to get 35 by 4 pi r square. This is my dr by dt. So I've gotten my value of dr by dt. Now I have to find out the rate of increase of its surface area. Now how do we write down the surface area of a sphere? It is written as 4 pi r square. Now I have to find out the rate of increase. So let me just differentiate this in terms of time. This would become 4 pi, and r square, it would become 2r dr by dt. Now from here we can use this value of dr by dt in this equation here, and then we can find out our dA by dt. That is exactly what we have to find. So this would become 4 pi into 2 into r. So now we can substitute the value of r as well here. R would become 7 dr by dt, 35 by 4 pi r square. So this becomes 7 into 7. So 4 pi and 4 pi would cancel out each other, 7 and 7 would cancel out each other, 7 5s are 35, and we get 10 centimeter square per minute as our answer. So again, a very simple question. This was also a question that was asked in one of the previous year JEE mains. So I hope you must have gotten the idea as to what level of questions are asked from this chapter. There are mostly simple. The only thing is you need to know what are the formulas of volume of a sphere, surface area of a sphere, and all these things you already have studied in your class 9th and 10th. So it is not a very big problem. Let's look at one more question. A spherical iron ball with a radius of 10 centimeter is coated with a uniform layer of ice. This ice melts at a rate of 50 centimeter cube per minute. When the thickness of the ice is 5 centimeter, find the rate at which the thickness of the ice is decreasing. So first of all, they've given us that there is a spherical iron ball whose radius is 10 centimeter, and it has been coated with a uniform layer of ice. So again, we do not know what is the thickness of that coat of ice. So let us assume for the time being that this thickness is x. So this is the thickness of the ice. This is my ice. The ice is melting at the rate, that means of 50 centimeter cube per minute. The ice, this portion here, it is melting at the rate of, they've given us, that means the rate at which it is changing is going to be negative of 50 because it is decreasing, right? So it will become negative of 50. So simply what we can do here is, first let us write down the volume of this spherical ball. What will be the volume of this spherical ball? It is going to be 4 by 3 pi r cube. What is my r going to be here? R would become 10 plus x r cube. So now let us find out the rate of change of volume of this entire system. So this would become dv by dt 4 by 3 pi, and upon differentiating this I'm going to get 3 times of 10 plus x whole square dx by dt. By applying chain rule I've gotten this differentiation. So now they've told us when the thickness of the ice is 5 centimeter. Now they've told us that x is equals to 5 centimeter. Find the rate at which the thickness of the ice is decreasing. That means we have to find out our dx by dt. They've given us our dv by dt, which is minus 50. So our dv by dt is basically minus 50. Now why is it minus? Because it is decreasing. We know the volume is decreasing, so it is going to be in minus sign. This would become 4 pi, 10 plus 5 would become 15 square dx by dt. Now what would be the value of dx by dt from here? Again dx by dt is going to come out to be negative, because the rate at which the thickness it is decreasing, that means our rate is also going to come out to be negative. So it would become minus of 50 by 4 pi into 15 into 50. Now you can simplify this as much as you want. This would become 5 3s, this would become 5 10s, and here you can further, this would become 5 3s, 5 2s, 2 2s, and so what do we get our answer? Minus 1 by 18 pi. This would be centimeter per minute, and this is our answer. So I hope you must have understood. These are very simple problems that are related to derivatives. Now we will be looking into the graphical functions of derivatives. So first let's start with increasing and decreasing function. And as the name suggests, what is an increasing function? A function which is going to increase throughout its domain or whatever interval it is been defined in. So let's say if I talk about this and this, I can see that the value of this graph is increasing continuously. That means it is an increasing graph. Now for decreasing, if the graph is decreasing, that means for any interval or in the domain in which it is defined, we can call it as a decreasing function. So here also the same things have been mentioned. A function f of x is increasing if for any x1 less than x2, f of x1 is less than equal to f of x2. So let's say if I have a graph, this is an exponential increase graph. So let's say this value here is my x2, and this value here is my x1. So I can see that at x2, what is my f of x2? My f of x2 is somewhere here and my f of x1 is somewhere here. So at any time, I can see that my f of x2 would be greater than f of x1. Whether I take the x1 and x2, be it at any points on the x-axis. If that is the case, then I can say that my function is increasing. And for decreasing, the same thing becomes reverse. For x2 being greater than x1, my f of x1 will be greater than f of x2. So this is my increasing and decreasing functions. Now talking about strictly increasing and strictly decreasing function. So what do I mean by strictly increasing? Here f of x1, again the things are going to be same. x1 is less than x2, f of x1 is less than f of x2. Here there is no equality here. However, here we studied about an equality as well, right? That means for a normal increasing graph, let's say if I talk about this graph, this is also an increasing graph. However, if I take my x2 here and if I take my x1 here, my f of x2 would be equal to my f of x1. This value is going to come out to be same. So this is an increasing graph. However, when we talk about strictly increasing, there is going to be no point where f of x1 is going to be equal to f of x2. So it is going to be increasing always. So that is this type of function, what we call it as strictly increasing function. Same thing goes for decreasing as well. For decreasing also, at some point, if my f of x2 is equal to f of x1, then I will call it as a decreasing function. However, if that is not the case, for a strictly decreasing function, there has to be no points where my f of x1 is is equal to f of x2. At all times, this equation has to be satisfied. Then I can say it is my strictly decreasing function. Now if we, again the same thing, if we look at the graphs of these functions. My increasing function, I hope you have understood these points now. At this portion here, you can see that at this portion my value becomes constant. So again, it is a constant. Had, let's say, I had this function in this manner and it would have decreased, let's say, at some point. That means this is now no more an increasing function. However, if I talk about such functions, let's say if I have a function in this format, now you can see at some point this function is decreasing, right? Now this function is not increasing in its domain. However, if I take certain intervals, let's say if I take this interval a from minus infinity to a, what can I say? This function is increasing. However, from a to b, this function is decreasing. So I hope you are understanding what I am trying to say. And for strictly increasing, it has to be increasing all the time. For decreasing, again, the same things work accordingly. So keep this thing in mind. Whenever certain intervals are defined, you can mention about the graph being increasing or decreasing in certain intervals as well. For example, this graph. Again, this graph, you couldn't have said that whether it is increasing or decreasing in its domain. Its domain is minus infinity to infinity. However, in its entire domain, at some portion it is increasing, at some portion it is decreasing as well. So you can identify whether it is increasing or decreasing in certain intervals as well. So like now from b to infinity, we can say it is increasing again. So keep this thing in mind regarding the interval portion as well. Apart from that, one more thing that you must remember, whenever you have a strictly increasing curve, if at any point you try to find out your dy by dx, it is going to be the slope, right? It is always going to be positive for a strictly increasing curve. For a strictly decreasing curve, or rather instead of dy by dx, I'm going to call it f dash x. So here my f dash x would always be less than 0, because you can see if I take the slope at any point in this curve, the tan theta of this is going to be more than 90 degree and it is going to be less than pi, right? So it is going to be negative always. So for strictly decreasing, f dash x would always be less than 0. However, for an increasing function, at some points the line is going to be constant. So at this point, if I try to find out my dy by dx, it is going to be a straight line, right? So what can I say? For an increasing function, my f dash x would be greater than equal to 0. At some points it can come out to be 0, right? It can be a straight line as well, and we know if it is a straight line, that means our slope is 0. For decreasing function, again, f dash x would be always less than 0. However, at some points it can also come out to be equal to 0. So keep these points as well in mind. Now talking about monotonic functions, a function is monotonic if in an interval it is always increasing or it is always decreasing. So again, the same thing, monotonically increasing means it is increasing, and for decreasing it simply means it is a decreasing curve. That means for x2 greater than x1, my f of x1 would be greater than equal to f of x2. And strictly monotonically increasing, again the equality is removed from both the cases. Now when we talk about monotonic functions, first of all, let's say again, if we look at this curve here, I can say this is a monotonic function because it is constantly increasing. I can say this is a monotonic function as well. I can say this is also a monotonic function because it is either increasing or decreasing in the entire interval. This as well is my monotonic function. Now let's say if I have a function which is, let's say, in this format. Let's say this is my curve. This point here, this is my C point, this is my B point, this point here, this is my A point. Now let's say this is a curve that I'm dealing with. Now what would I say about this curve? From interval, I will define this curve in different intervals. So keep this thing in mind. Try to define, whenever you find a function, you must define it in certain intervals. So from A to C, what can I say about this function? From A to C, at some portion it is increasing and then it starts decreasing. That means it is not monotonic, right? Because for a monotonic function, it has to be either always increasing or decreasing. Here, it is not the case, so that means it is non-monotonic for A to C. Now, if I talk about from A to B, what can I say from A to B? From A to B, I can say that the function is always increasing. That means I can say it is monotonically increasing. And of course, at any point, it is, I can see that my f of x2 is not going to be equal to my f of x1. So I can say it is strict as well, strictly monotonically increasing. However, from B to C, if I look at it, it is constantly decreasing. That means from B to C, I can say my function is monotonically decreasing. And since at no point I can say that my f of x1 would be equal to f of x2, so this would become strict as well, strictly monotonically decreasing. So exactly the same things have been mentioned here. A function is said to be monotonic in A to B if it is either only increasing or only decreasing in A to B. From A to C, the function is non-monotonic, as I had taken the example of that graph. This graph, this is my A, this is my C, and this is my B. From A to C, this function is not monotonic. In the interval A to B, the above function is monotonically increasing, and from B to C, the above function is monotonically decreasing.